Okay, so we just talked about different ways of comparing the equivalence or not equivalence of outcomes for two different groups, two different rows. Um, right, the three different ways that we talked about doing this were the risk difference, the risk ratio, and the odds ratio. We've already talked about the first two. We talked about the risk ratio and we talked about the risk difference. We talked about the type of situation that you might use one rather than the other. Although we also mentioned, right, there's no need to sort of to exclude one, right? You could, if you felt it was informative, right, sort of report both of them to create a more holistic picture of sort of what's going on. Um, so now we're gonna finish up this week's lecture by talking about the odds ratio, and then we'll take a look at some SAS code. We've been doing some hand calculations just to kind of get comfortable with kind of where these numbers are coming from. But of course, at the end of the day, we'll have SAS do it for us. So we'll go ahead and look at some SAS code for doing that. Um, Now, the example we're going to work through is the same example we were working with previously. That is, right, that physician study. We had an aspirin group and a placebo group, and we looked at whether or not these physicians that were enrolled in the study either had a heart attack, a myocardial infarction, or they didn't. All right, so let's go ahead and talk about odds ratios. Before we talk about odds ratios, we have to talk about the notion or idea of odds. Right, odds is a term that a lot of us use and we see fairly frequently. Right, you go to the racetrack, they talk about odds. You may or may not be into sports betting. They talk about the odds of a team winning. The term odds is used a lot, and I guess in a betting context. There's also that sort of popular saying, right, when something kind of unexpected happens, um, right, we say like, "Wow, what are the odds of that happening?" And and in a way, that saying kind of gets at maybe one of the problem with odds is that sometimes it's used or thought of as being synonymous with probability. That is, right, when we say, what are the odds of that? We're really saying that we think the probability of that happening is very, very small. That is, we're using the word odds, but I think most people are kind of interpreting it in that particular context as a likelihood or a probability, and they're not, right? So that's something we really want to be aware of. We'll talk about situations where they are interchangeable, but they are not always interchangeable. And there are a number of sort of real life examples, um, more so in kind of like, I don't know, like mainstream kind of news uses or interpretations, let's say academic uses. But there certainly are instances where odds or odds ratios are interpreted as probabilities or probability ratios um, with sort of distorted results. So let's go ahead. So the odds of an event are what? The odds of an event are defined mathematically as, right, the probability over 1 minus the probability, right? So if something has a 50% chance of occurring, then its odds are 1. If something has a 75% chance of occurring, its odds are 3. Right? Should make sense. Now, the odds ratio of two events, or say two groups, actually is maybe a better way of saying it, is defined as, because we're still talking about the same event. So here we're talking about maybe, right, the event being a heart attack. So we have sort of the odds of heart attack for, say, the placebo group over the odds of heart attack for the aspirin group, right? So we're looking at a ratio of odds, and we use traditionally the Greek symbol theta to denote that odds ratio. Now, in this case, note that a test of no difference between groups is equivalent to, right, the null hypothesis. So right, if the odds are the same between the two groups, right, then that means the numerator is same as the denominator. It means that that odds ratio is going to be 1. Now notice the odds being the same is equivalent to the probabilities being the same. So in a lot of ways, this is similar to kind of what we've done with the risk ratio. And so if we actually want to do this hypothesis test, what do? Right, well, we want to test the true odds ratio. So, right, we don't know the true odds ratio. We have to take a sample. We take that information in our sample. We come up with we'll call it theta hat, a sample-based odds ratio, which becomes our best guess for the true but unknown odds ratio. Now, how do we come up with a sample-based odds ratio? Well, we just use the formula for the odds ratio. It's just, right, we don't know what those pi's are. We don't know the true probability of heart attack, so we replace it with the sample-based probabilities, right, the sample proportions. Okay, so odds ratios are interpreted multiplicatively, just like risk ratios are. So in our example, right, the myocardial infarction example, the odds of a heart attack for the aspirin group is, well, the probability of a heart attack was at 0.009 over 1 minus 0.009. Put that into a calculator, you get about 0.009. The odds of myocardial infarction for the placebo group is 0.017 over 1 minus 0.017. You put that into a calculator. Hey, a little deja vu, you get 0.017. So the odds ratio of the placebo to aspirin is 0.01714 over 0.009513. Put that in a calculator, you get 1.83. So we would say that the odds of myocardial infarction for the placebo group is 1.83 times that of the aspirin group. We would not say that the probability of myocardial infarction for the placebo group is 1.83 times that of the aspirin group. That would be technically wrong. Although we'll see in this particular example, it's very, very close to true. But that's not always the case. So we do not interpret odds ratios that way. We interpret them exactly as it is in that bullet point. So this would be the part of class where I say, 1.83, where have I seen that number? Where have I seen that number before? I have a haunting sense of familiarity. Does anyone, what's the name for a haunting sense of familiarity? Oh yeah, deja vu. Where have we seen that number? And then, right, we just sit there and stare at each other awkwardly for a few minutes before one of us kind of, breaks the stalemate and observes that this 1.83 is very, very, very similar to the 1.82. That is, if you go back to the last lecture where we calculated the risk ratio for this example, we calculated the risk ratio to be 1.82. So in this example, the odds ratio and the risk ratio are very, very close to one another. It's not true in every example. It's true in this example. We can get a sense of why that's the case by looking a little more closely at the following formula. So we could do a little bit of algebraic rearranging to write a formula for the risk ratio in terms of the odds ratio, right? And so that's what it is. So what do we observe? Right, the N21 is what? The N21 is the number of people in that second row, whatever the second row was, either aspirin or placebo, but the number of people that had the event of interest, in this case the heart attack. The N11 is the number of people in the other group that had the heart attack. So notice that if both of those numbers are very, very, very small, right, that is if it's very rare, if it's very unlikely to have a heart attack, which in this case it appears to be the case, that N21 will be very small, N11 will be very small. Both those fractions will be very close to 0. And so, right, we'll have 1 plus something close to 0 over 1 plus something close to 0. That's going to be close to 1. And so the risk ratio is close to the odds ratio, right? So what can we observe? We can observe that these numbers are certainly not the same, right? There is this difference factor. But when we're dealing with an event that's very unlikely or very rare, the risk ratio and the odds ratio will tend to be very, very, very close to one another. Now, a pretty widely used rule of thumb is that whenever the probabilities of interest are 10% or less, right? And that's certainly the case in our example. The probability of myocardial infarction for one group was a little less than 1%. For the other group was a little less than 2%. So that's both of them are well under 10%. When the probabilities of interest are 10% or less, then we say that the odds ratio is a good approximation of the risk ratio. However, if we're dealing with events that have probabilities more than 10%, the odds ratio and risk ratio are going to be different enough from one another that we shouldn't be considering using them interchangeably. Now, a nice little shortcut formula. A lot of times we will use SAS, and I'll show you some code very soon to use SAS to calculate this. And we did the calculations already in a previous slide. However, there is a kind of nice shortcut calculation, right? When you have kind of like ratios of ratios, not surprisingly, a lot of things kind of cancel out. And so again, it's just algebra and just canceling a lot of n's. But ultimately, you have this pretty easy to calculate shortcut formula where we can show that theta hat, the sample-based odds ratio, is n11 times n22. So that's kind of the, I guess we'd call it the right diagonal. It's the upper left part of our cell times the lower right part of our cell over n12 times n21, right? So that would be the upper right times the lower left. And so, right, a relatively easy calculation for coming up with an odds ratio by hand, or well, you still would use a calculator, but you could use a calculator and not have to use SAS, or right, not do it quite as laboriously as you might using the sort of definitional formulas. All right, so that's kind of the idea behind the odds ratio. How might we do some inference? And of course, right, when we're talking about inference, we could do hypothesis tests or confidence intervals. Here I'm going to talk about confidence intervals because confidence intervals, right, give us a range of plausible values, which is very, very nice to have. Right, it sort of enhances or augments our descriptive statistics. And then we'll see, of course, that we can use this confidence interval to also do a hypothesis test. So how do we do a confidence interval for the natural log? Well, it turns out that this sort of script f is just going to be shorthand for the natural log of our odds ratio. Turns out that converges to a normal distribution at a faster rate than the actual odds ratio itself. And so what we're going to do then is we're going to actually work on the log scale, not the original scale. This is actually a pretty common trick when you're working with ratios of any kind. That is, I've used in some previous projects. I've used this trick when I'm looking at it's done less commonly, but I found it useful in one project. I've seen it used in other contexts. Here we're looking at like a ratio of odds, but right, we could also look at maybe in some example a ratio of means, and in that case we could use this kind of same trick of taking right the log of the ratio of means. So right, a lot of times when you're working with ratios, taking a log is a nice trick. So it's a little bit more general than just this example right here. So what we do to build our confidence interval is we take the log, we go on the log scale. Right, we can show mathematically that the variance or an estimate of the variance for the odds ratio on this log scale is kind of a cool looking formula, right? It's just 1 over n11 plus 1 over n12 plus 1 over n21 plus 1 over n22, right? So those are essentially our 4 cell counts. So we just reciprocate our 4 cell counts and add them up. So we have a best guess. We have a variance estimator, and there's a result that says that at least for a large enough sample, this thing follows a normal distribution. That's all we need to build a confidence interval, right? So now our confidence interval, very, very, very familiar formula, our best guess plus or minus a critical value times the standard deviation of our best guess. So let's do an example, right? Let's see how these calculations would be for the example that we've been working through. All right, so the calculations are relatively straightforward. So we found out from our previous slide that our sample-based odds ratio, our theta hat, was 1.83. So right, again, we could sort of show mathematically that in terms of getting that normal approximation more effectively, we're better off working on the log scale. So first step is to take the log of 1.83, put that in a calculator. I believe you get 0.6043. So that becomes our best estimate for the log odds ratio. Now we want to make a confidence interval for the log odds ratio. We need its variance, right? We saw the formula in a previous slide. The variance is, right, 1 over each of the cell counts added up. So 1 over 104 plus 1 over 10933 and so on. We do all that. We get 0.0151. So a 95% confidence interval for the log odds ratio, for the log of the true odds ratio, is 0.6043, right? Plus or minus our critical value. Critical value for 95% is 1.96 times the standard deviation. Standard deviation is just the square root of the variance, so square root of 0.0151. So there's our confidence interval. But again, that confidence interval is not useful. It's not informative. It's on the log scale. We want it on the actual scale, right? We don't care about log odds ratios. We care about actual odds ratios. So how do we go back to our original scale? Well, we do the reverse of the log transformation. We exponentiate. So we exponentiate both endpoints of that confidence interval, and we find out that a 95% confidence interval for theta is going to be between 1.438 and 2.328. So I believe I'm going to interpret that on the next slide. Yeah, so there's our interpretation. We would say that we are 95% confident that the odds, right, not the likelihood, the odds of myocardial infarction for the placebo group is between 1.438 and 2.328 times the odds of myocardial infarction for the aspirin group. Now, that's a confidence interval. Confidence intervals are nice because, right, we'll see not only did they let us do statistical inference, they give us like this nice range of plausible values. But what if we did want to do statistical inference? That is, right, we wanted to know whether or not one group is significantly different than the other. Well, remember, we did that by looking at a hypothesis of whether or not the odds ratio was 1 or not equal to 1. And we can do that by looking to see whether 1 is included or not included in our odds or in our confidence interval. In this case, right, our confidence interval does not include 1. So we would say, even though we don't know exactly what the odds ratio is, we got it narrowed down. It's somewhere between 1.43 and 2.328. That entire range of values is more than 1. And so that's sufficient for us to conclude, right, using an alpha of 0.05, that we think that the odds ratio is something other than 1. All right, so at this point we've talked about these three different things: risk difference, risk ratio, odds ratio. And of course, we've talked about how to calculate them by hand, but let's go ahead and see how we might use SAS to streamline that process. So here we are. I'm just creating a data set. Nothing too profound here. We should be comfortable with this code. right? I have a treatment variable, placebo or aspirin. I have an outcome variable, either a myocardial infarction or none, no myocardial infarction. And then this count variable. So the count variable, and particularly how it's used in proc-freq, might be something that's new to us. I know we did a lot of proc-freq in stat 511. I'm not sure that we used the count variable in 511. The count variable allows us to be more terse, to be more compact when we're trying to embed a table into a data set, right? So technically, our data set consists of, I mean, looking at those numbers, what would it be? A data set consists, I think, of more than 22,000 physicians. So in theory, if we did a data set, if we tried to actually build a data set, it technically would have 22,000 lines, right? That's a lot of lines. But like, there's a lot of redundancy, isn't there? Because there's 22,000 lines, there's 22,000 physicians, but right, all of those physicians really just fall into four groups, don't they? So those 22,000 physicians, right, in which case we might make a data set that has 22,000 lines, fall into one of four groups, right? There's two possibilities for the treatment they're on, and there's two possibilities for the result. So the total number of groups is 2 times 2, which is 4. So we can write that information more compactly by just writing each of those four groups and then using a count variable to signify how many physicians fall into each of these groups. We could then use proc-freq. So proc-freq we're familiar with. There's a table statement. That's what does the heavy lifting in proc-freq. You put the row variable first and the column variable second. Row then column, RC cola. And then here we use this count variable. And so if we want to use some auxiliary variable, in this case count, to tell us how many observations are in each group, we use the wait statement. So if we do wait count, that's basically telling SAS that, right, if you want to know the number of people, the number of physicians in each group, look at the count variable. And so this is what we get. So a lot of information there. The default table is a bit cluttered. If I look in the upper left of the table, right, I see the words frequency, percent, row percent, column percent, right? So it's basically, what is SAS telling us? It's telling us that in each of the informative cells there's four numbers. The top number is the frequency, the number of doctors that had a myocardial infarction or that fall in that particular cell. The percent, that's the percent of the total overall physicians, the 22,071 that fall into that cell. The row percent is a conditional probability. So that's basically saying, right, of all the people in the aspirin group, if I'm looking at that top left cell, of all the people in the aspirin group, what percent had a myocardial infarction? And then the column percent is also a conditional probability. It's just looking at the sort of the up and down, the vertical conditional probability. So if I was interpreting that column percent, that 35.49, that's basically saying that of all the people that had a myocardial infarction, 35% were in the aspirin group. Now, a lot of those numbers are not typically meaningful. So what we'll see in the next slide is that there's ways to suppress some of the information. Typically, what we're interested in is the actual frequencies, how many actual observations are in each cell. That's often nice to know and makes for some nice descriptive statistics. And then the row percents, right? Because the row percents are actually what's being compared, right? So the row percent is 0.94 and 1.71. Those are really the percents that we're in most cases interested in comparing, right? 94% of the people in the aspirin group had a heart attack. 1.71% of the people in the placebo group had a heart attack. So is one of those numbers more or less than the other? So we could make a cleaner table by using the slash command in the table statement. So I can do slash no call, that'll suppress the column percents. I could do slash no row, that will suppress the row percents, although I usually like to have the row percents there. We could also do slash no percent, that will suppress the overall percents. Right, so here's a cleaner looking table. Here I used no call and no percent, and so now I have just the frequency and the row percentage. So this is a little cleaner, focuses just on information that I care about, gets rid of some of that extraneous information that I don't care so much about. Now, one little side note. When I go back and look at that table, I'll see that SAS put aspirin on the top, placebo on the bottom, put myocardial infarction on the left, put none on the right. Why did SAS do it that way? How does SAS, by default at least, order the rows and the columns? SAS does it alphabetically, or right, if you have numbers involved, alphanumerically. So aspirin comes before placebo alphabetically, so that's why it's aspirin then placebo. Myocardial infarction comes before none alphabetically, so that's why it's myocardial infarction before none. We need to be aware of SAS's defaults, particularly when we start working with larger tables, because these defaults may or may not be constructing the table the way we would like it constructed. And so, right, if it's not building the table correctly, we need to not only be aware of how it's doing it, right, what default it's using, but how to override those defaults, which we'll start learning how to do in future lectures. For now, we just want to build an awareness of what SAS is doing by default. Now, what about inference, right? We talked about these risk differences. We talked about these risk ratios. We also talked about these odds ratios, right? How can we get these things? Well, again, it's just a keyword in the table statement. If we put the risk diff keyword in the table statement, we'll get risk differences. And if we put the measures keyword in the table statement, we'll get odds ratios. And of course, you could put both keywords in the table statement and get, right, all of that information. So here is some output from the risk diff statement. It actually will do it for column 1 risk and column 2 risk, right? Because SAS doesn't really know, right, is what you're interested in, myocardial infarction, is that in the left column or the right column? I'm not really sure, so I'm just going to give you information from both columns, and then it's up to you to pick the relevant one. Now, we saw that SAS put myocardial infarction in the left column, in column 1, so that's the column we want to focus on. Right, so risk in this case is just like the sample probability or sample proportion. So remember, row 1 was our aspirin, so a little less than 1% of our aspirin group had a heart attack. Right, we look at that row 2, that's our placebo, a little less than 2% of our placebo had a heart attack. Right, and then that bottom row shows us the difference. And then we go over to the right, we get a confidence interval for that difference, right? So, right, we could look at the confidence interval for that difference, right? We can see that that confidence interval does not include 0. And so we would say that, right, that the risk of heart attack is significantly different for these two groups. Easy enough? All right, let's go take a look at the output for the measure statement. So there's a lot of information you get from the measure statement. All that stuff up top where it says statistics for table of treatment by outcome. We haven't talked about any of that yet. We'll see. We may or may not talk about that later in the class, depending on kind of how I feel like our time is working out for us. But more importantly, if we look at the bottom if we look at the bottom, then we'll see the odds ratio, right? And so it, right where it says case control and says odds ratio, that's going to give us the actual odds ratio, right? It says row 1 over row 2. So this is the odds ratio of aspirin over placebo. And we see that it's 0.5458. So we would say that the odds of a myocardial infarction for the aspirin group is 0.5458 times that of the placebo group. We can get the risk ratio by looking at where it says cohort. So where it says cohort is giving the risk ratio. Right? Again, SAS is not sure what the outcome of interest is, so right, gives us both column 1 and column 2. We're interested in column 1. Column 1 being myocardial infarction. So here we would see that the, and I think we calculated this in the previous slide ourselves. We saw that that the probability or the likelihood of a myocardial infarction for the aspirin group is 0.5501 times that of the placebo group. Now, if you wanted, instead of the aspirin group relative to placebo, you wanted placebo relative to aspirin, we could, of course, just do 1 divided by, say, 0.5458, and that would sort of flip the odds ratios for us. All right, so I think that wraps up our SAS code. It also wraps up our introductory discussion of descriptive statistics in a sort of basic 2x2 table. We'll start going a little bit deeper when we get to next week's lecture.